Welcome to Black Hat Briefings, held November 21st through the 22nd, 2001 in Amsterdam. This is videotape number V10, injectso, modifying and spying on running processes under Linux.
Okay, we're going to have to get started because the speech runs long, so just want to make sure that we get through as much of it as we possibly can. Okay, so my name's Shaun Clowes. I work for a small security consultancy in Sydney, Australia called Secure Reality, and I'm here today to talk about a couple of things actually. I'm going to speak about a particular tool which I've written called injectso, but I'm also going to speak more generally about various ways of modifying and spying on processes running just generally under Unix, but injectso itself at this stage runs on Linux and Solaris, which is why the speech is subtitled the way it is. What are we going to talk about in the speech? In part one, we're going to firstly talk about a tool called InjLib, which some of you might be familiar with, which works under Windows. Then we're going to speak about what injectso is and why it's vaguely related to InjLib. We're going to talk quite a bit about ELF, the ELF file format, the binary file format. Then we're going to speak about program and process modification techniques under Unix, that is, various techniques which are known, which are which are like the forefathers of injectso. And then in part two, after the break, we're going to speak about the differences between injectso and InjLib, how the two work, the conceptual similarities and the implementation differences. Then we're going to speak about the details of how injectso works, the tool injectso. We're going to speak about intercepting dynamic function calls, which is the main use, which is one of the cool features of something you can do with injectso. Then we're going to speak really shortly about defending against injectso, which is not exactly difficult. And then we're going to speak about the future of injectso and these sort of techniques anyway. Before I actually start up, because the speech does run quite a bit long, it would be really good if I could get an understanding of where you guys are and what sort of stuff you guys have done, so I don't waste your time talking about stuff you already know. Who here is really familiar with Unixes? Okay, that's basically everyone. Who here has done systems programming under C or something like that under Unix? Okay, who has an understanding of ELF, an internal understanding of the ELF file format? Okay, cool. So I'm going to have to do most of it. If various sections are boring you or you think they're obvious or whatever, please say so, or I'm not speaking loud enough or whatever, because I will be forced to rush through various sections of it so that I can get it all done. But okay, so what's InjLib is the first question. Well, InjLib was actually a tool which was developed in the Windows Systems Journal in 1994. It's a very old bit of technology, and it was written by a guy named Jeffrey Richter, who some of you might be familiar with. He's a Windows NT guru, and has been around for a very long time. And basically what InjLib does is a process which you can use to inject the DLL, a dynamic link library, a Windows dynamic link library, into another process under Windows. All the versions of Windows. The injection of the DLL has no effect on the target process. That is, the target process continues running as normal, but the DLL can do whatever it wants once it's inside the remote processor's address space and executing inside the remote processor's space. And the DLL can also be passed information about the target process so that it can manipulate the target process in various ways and do various interesting things. So some things to note about InjLib. The process is extremely trivial under Windows. In fact, the entire process is complete in well less than 50 lines of code. But it's a very impressive feat because it allows you to do a hell of a lot of low-level systems programming type stuff under Windows. The technique is very widely used, as you might imagine. It's used in tools you might be familiar with include pwdump. Versions 2 and 3 use injectdll to get inside a system process and read information. Getadmin, that famous old exploit for Windows NT, use this technique. Fport, which I believe has been renamed since, but that's Foundstone's tool for checking which processes are listening on which ports, and basically every spy application you've ever heard of. If you're familiar with Windows systems programming, you would be familiar with the various spy applications, and they basically all use this technique. The basic process which InjLib uses under Windows NT is that they find the address of a certain system function which is used to open a DLL. There's a function provided in Windows NT which you can call with the name of a DLL, and it will open the DLL and map it into your address space. That they then attach to the process as a debugger, allocate memory inside the remote process, copy in a function from their own address space to the remote address space, which will call the DLL loading system function to load a particular DLL. Then they create a thread which starts inside the remote process, which starts running at the injected function, and that function then loads the DLL. So basically, you copy code into the remote process, which calls the normal load library function. Step one is finding the address of the system function provided to load libraries, basically, and then the DLLs under Windows are dynamically loaded using a function called load library A. The function which InjLib copies into the remote process needs to know the address of this load library A to call it to get the DLL loaded. So the first step is finding the address of this function. And obviously the copied function can't rely on, it can't be compiled in to just call load library A. It has to know it at runtime where load library A is. Load library A is in kernel32.dll, which is one of the main DLLs of Windows, probably the main DLL of Windows. All Windows applications have kernel32.dll mapped into their address space, and it's also safe to assume that all Windows 32 functions have this DLL mapped at the same address. So if you work out the address of load library A in your process, it's going to be at the same place in the remote process, which is what InjLib relies on. So InjLib loads up the library kernel32, finds out the address of the load library A function inside its own process, okay, and then it knows where the function is going to be inside the target process, which it plans on injecting a DLL into. Okay, so that's step one. In step two, now that it knows the address of the function, it's going to need to call inside the remote process. It attaches to the process as a debugger, which is obviously a trivial operation under basically every operating system these days. In code, it's just open process with all privileges to do whatever you want to with the process, and you get a handle to the process. Obviously, this is a restricted function, and you need to have the SE debug privilege to debug a process which is owned by another user, or you can use it on any of the processes which you own without any special privileges. In step three, you allocate memory inside the remote process, which is going to store the copied function, this function which you're going to copy in, and the arguments to the copied function, because you need to provide some information to the function which you've copied in there about where load library A is. In code, Windows is very helpful with this entire process. As we'll see, particularly when we start looking at the Unix side of things, Windows is extremely helpful. You can actually ask Windows NT to allocate memory for you inside a remote process, as long as you have a handle to that process. So in this case, we've just got virtual alloc x. You pass in the handle of the process, you say how many bytes you want to allocate inside the remote process, and that you want the memory to be executable and read-writable. So we've now got some space in which we can do work inside the remote process. Step four is we copy the function and its arguments into the process. So in code, all we do is we just we choose an address inside our process space, how much we want to copy, and we choose an address inside the remote process to copy it. So all we do is InjLib has a function inside it which takes in an argument of where load library A is and the name of a library. Okay, it takes this function and it copies this function from its address space into the remote address space, and this function then is code inside the remote address space which can load a DLL. In step five, we create a new thread in the remote process, and we start it at the address of the injected function. So we've got this code inside the remote process. Now we need to start it to get the library loaded by that code. And to do that, all we do is we create a remote thread. And again, what we'll find is that this is really trivial under Windows, because Windows helps you out an incredible amount here. All we have to do is we have to start this code, and we have to pass in the address of a structure inside the process, which we put in there with the memory we allocated. And it contains information about where load library A is and the DLL name to be loaded. So in code, all we have to do is we can go, Windows actually provides a function called create remote thread, and we can pass it a handle to a process, and it will actually create a thread for us inside a remote process. So it's creating a Windows NT thread inside this process, and it can start it at any address you'd like to, at the address of any function you'd like to. So we've injected a function, so we start it there, and then we can also pass in a pointer to the arguments, which will be the argument to the function which is called when the thread is created. So at that point, we're almost done basically. The injected function is now running in a separate thread, so it has no effect on any of the existing process. The process continues running. And the injected function is now executed, and load library A is called by the injected function using the function pointer to load library A and the DLL name arguments. So that's it basically. You've now, in about less than 50 lines of code, you've now injected a DLL into a remote Windows NT process. And obviously the result of that is that injecting a DLL under Windows is easy, it's short and it's safe. We're going for time. Okay. So once you've injected a DLL, what's the point? Why the hell would you want to inject a DLL into a remote process? There are a hell of a lot of applications for this technique, and for those of you who are systems programmers, you'd probably see a lot of them. But once you've injected this DLL, you can literally do whatever you'd like to. This DLL can call and do whatever it would like to, including calling all the standard C functions, load up other DLLs, doing whatever it likes to inside the remote process's memory space and execution space. So various examples of what existing applications do. They modify internal memory structures in the process to make it behave differently. Another example is, I'm not sure whether you guys are familiar with window blinds. It's an application which changes the appearance of all the windows under the Windows operating system. So you could inject a DLL and change the look of all the windows, like make it themable and all that stuff. You can call API routines, which you normally wouldn't be able to access, like privileged API routines, from inside the process itself. You can use open IPC channels. The process might have privileged IPC channels open where you can't open another one. So you could use the IPC channels inside the remote process without affecting the process. You can patch the program at runtime and make it behave incredibly differently. And basically, you can just do anything you want to. You're inside the remote process. You can do anything that process can do. And that's a very powerful ability to have. You can do a lot with it. So I guess the question then is, how is InjLib at all related, or whatever, to injectso, which is what this speech is all about? Well, injectso is basically like InjLib for Linux and for Solaris. So it's a Unix version of this injecting a DLL sort of technique. And I guess the closest relationship to a DLL under Unix is a shared library, which is basically exactly the same thing. And what injectso does is it injects a shared library into a remote Unix process. Once the shared library has been injected, injectso also provides some support code to help the injected shared library do interesting stuff to the remote process. So basically it makes it easier for the injected shared library. But I'm going to go into much more detail about that later. What I'm going to speak about before that is I'm going to speak about various other techniques for modifying processes, modifying and spying on processes, so that we can see what already exists and what's different about injectso. But I'll go into hideous amounts of detail about how injectso works and what you can do with it shortly. Actually in the second half. So I guess the one question we have to actually ask ourselves is, what is this of interest to us? We're here at the Black Hat briefings. It has to be, well, obviously it's security-related conference. How has this got anything to do with security? And it's funny because when I first started working on injectso, I didn't work on it from a security point of view. I wasn't interested in the security ramifications of it. But obviously the ability to modify processes and programs while they run or statically, and the way they behave has pretty clear security ramifications. I mean, it's been seen in the past for sure. You can patch vulnerabilities, as Halvar Flake has demonstrated fairly clearly at the other Black Hat briefings for fixing vulnerabilities in Windows NT software. So you can patch vulnerabilities at runtime while it's executing or statically. And you can also do the opposite and do the Black Hat style thing and backdoor or otherwise modify processes in a nasty way. So that's sort of like virus and backdoor style things. So that's basically why this is interesting to us. So fair enough. We've talked about InjLib and Halvar's spoken at length about how you can do this sort of stuff under Windows. How can you do it under Unix? What sort of techniques are there for modifying programs and processes under Unix? There are heaps, and a few which we're going to speak about today. I mean, there are a wide variety on the internet and stuff, but a few which we're going to speak about because they're interesting today are binary patching, that is patching the binaries while they're on disk and making them do different things, and fixing vulnerabilities and introducing subverting processes. The dynamic loader environment is one of the easiest ways of doing this sort of stuff, which some of you guys might be familiar with, but I'm going to present some different techniques along those lines. And then in-core patching. So it's almost like simple binary patching, but you do it while the process is running. So most of what I'm going to say about modifying programs and processes is going to be meaningless unless we have an understanding of how programs and processes exist on disk under the Unix operating systems. So basically, we'll need an understanding of the internal structure, which is why I'm going to speak for a little while about ELF. ELF is the executable and linkable format. It's a bit like PE, the portable executable format for Windows, but it's basically, it's used under almost every recent Unix uses the ELF format because it's very flexible. It was originally by the Unix Systems Labs. It's a very old standard, and since it's been adopted by the Tool Interface Standards Committee, and Intel are the big proponents behind the ELF file format. So when you've got ELF files, you actually have three different types of ELF files. You have relocatable files, which might be commonly known as object files, and these are files which contain executable code and which are ready to be linked with other relocatable files in order to create an executable or a shared object. An executable is obviously something which you can run from the command line. It's designed to have a certain address where it's loaded and starts executing, and it may or may not require certain other shared objects. Shared objects are baseless. Very much like baseless executables, they have almost all of the features of an executable, but they can't be executed. They're designed to be used at runtime by executables. For our talk, for our purposes, only the last two are relevant, so I'm not going to speak much about relocatable files, and I'm going to concentrate on executables for what we're covering. So the ELF specification describes two separate views of an executable. So when you've got an executable on disk, or any ELF file on disk, there are actually two separate views which you can take on it when you're working with it, modifying it. The two views are a linking view and a loading view. The linking view is completely static, and it's a very meaningful view which is designed to be used by linkers and other things which work with ELF files to describe their internals really clearly. The loading view is a much, much simpler view and is only used at runtime to load the actual executable into memory and start it running, or to load the shared library into memory as relevant. So taking a quick look at that, when you've got an ELF file, the first thing you have in the ELF file is an ELF header, and then the ELF header gives you a pointer to the section headers, which are the linking view, and the program headers, which are the execution view. Interestingly enough, in relocatable files, this stuff will never exist. In executable files, this doesn't have to exist, nor does it have to exist in shared objects, but it normally does. So you've got the sections which point into the various file. It's like an index into the file, and you've got the program headers, which are also an index into the file, but there are much fewer of them, and that'll be clearer as we go on. So the linking view. As I said, the linking view is a meaningful view of the executable, and it divides the executable into sections. As you can see here, each section has a name, and they can actually be named whatever you want, but these are some of the common and more interesting sections inside an ELF executable. Each section has a name and a type of the various types which are defined in the ELF file format. A requested memory location where the section would like to be at runtime, if it is going to be at runtime at all. And permissions, which it would like if it does go runtime, writable or executable, if this section is meant to be loaded at runtime. So some important sections for what we're talking about. We're actually going to be speaking a lot about the dynamic linker or the dynamic loader, same thing, but we're going to be speaking a lot about the way it functions, both in terms of injectso and in another technique which we'll be talking about. But so that's why I'm concentrating on these sections which are relevant to the dynamic loader. If we look here, we've got the interp section. the interp section requests a certain dynamic loader which you'd like to be used to load this executable. The dynamic section provides information which the dynamic linker or loader needs in order to successfully work with this file. It's the critical section for any dynamic executable. We've got the symbol table and the dynamic symbol table, which are basically static symbols which don't need to exist at runtime, and dynamic symbols which need to exist at runtime, because they refer to symbols which need to come from external places like shared libraries which need to be loaded at runtime. You've got the string tables. Again, you've got the static string table, which refers to the sim tab. You've got the dynamic string table, which refers to the dynamic symbol table. You've got the procedure linkage table, which is what allows you to call functions which are external to your executable. So if you've got a function in libc, you call it through the PLT, and we'll talk about that more later. You've got the relocations for various sections. Again, we'll talk about that more later, but that's important for the dynamic linker. And you've got the text section, which contains your code, actual executable code of the program. So that's a linking view. And as I said earlier, not all of the sections which are described in the linking view need to exist at runtime. For example, some of them are debugging information. Other bits are meant to be used by the linker when it's creating an executable. And that's the difference between the link time and the runtime view of the executable. The loading view, which is the runtime view, is much simpler, and it divides the executable up into segments. All of the segments are meant to be loaded into memory when this executable is loaded in. So that is, there are no sections which don't need to be loaded into memory will be referenced by a segment. So you've got these, as you can see, there are generally much fewer segments inside an executable. These are some examples of the common segment types you'll see in an executable. Segments have a simple type, that's interp, load, dynamic, no name, a requested memory location where they'd like to be at runtime, and permissions for that memory page, readable, writable, or executable. So you can specify exactly what should be possible on this memory at runtime. Looking at the ELF segment types, there aren't actually all that many, but there are only three which we're really interested in. There's an interp segment type which is an exact correlation to the interp section, and it specifies the memory address of a string which says the dynamic linker we'd like to use when this executable is loaded and executed. We've got the dynamic segment, which is the same as the dynamic section, and it contains information which the dynamic loader needs at runtime to make this executable work. And then you've got you have quite a few normally loadable segments, normally two, which specify just bits which should be loaded into memory, just bits of executable code or other things which need to be present in memory, sections of the executable file. So if we compare the two views, we've got the linking view over here and the loading view over here. We can see various sections which correlate exactly. The interp section correlates exactly. The dynamic strings and the dynamic symbols go into just a load segment, and you can see the permissions down here of what the memory pages will have at runtime. The dynamic section, it exactly correlates to the dynamic segment. You've got a data section which goes into one of the loadable segments, and then you've got a number of sections which don't make it at all, and they don't need to exist at runtime. That was exactly what I was saying. The section table is all about meaning. It's all about describing information about the executable. It's meaningful, and that makes it completely irrelevant at load time. At load time, there is no meaning required anymore. All of the meaning which is needed by the dynamic linker is stored inside the dynamic segment, and everything else is completely superfluous. And that actually means that all of the section information from an executable, every single bit of it, can be stripped after you've constructed that executable. If you guys are familiar with strip, a common Unix tool which you use to strip out symbolic information, it removes all of the symbol sections, but it's actually quite possible to remove all of the sections, which will well and truly break things like object dump, GDB, all that sort of stuff which rely on the meaning provided by the section view. So just quickly, when we're loading and executing an ELF executable, given that we've got this understanding of ELF, what actually happens when we're loading and executing an ELF executable? The process I'm going to describe here, I have to say, is actually textbook stuff. This is the way an ELF file is meant to be loaded and executed. If you ever look at the loader under Linux or something like that, you'll see that it's not done anything like this. But this is the theoretically how it's meant to happen. The file's opened by the kernel. A file descriptor is passed to whatever the dynamic linker, which was specified as required in the interp segment. So the kernel finds the interp segment, works out, okay, it needs this dynamic loader, loads up that dynamic loader, and then passes it the file descriptor to the file. The linker reads in the file segments and loads them at the requested addresses inside the segment table. And then the linker finds and processes all of the information inside the dynamic segment. So I guess because I've kept referring to the dynamic segment, I better explain what's in it. And it's actually really important because injectso makes a lot of use of the dynamic segment, and one of the other techniques also does too. Basically, the dynamic segment is a table of records containing information which is critical to the dynamic loading or linking process. It allows the dynamic linker to find out information about the executable, only relevant information about the executable, very quickly, without a section table, without any of that stuff. And each record's very simple. It consists of a type and a value. So some interesting dynamic segment tags or dynamic segment records. DT needed, which specifies the name of a required shared library. So this is a library I want to be loaded in. The jump rel specifies the address of the relocation entries which are associated with the PLT. So that's basically specifies the address of a list of all the functions which need to be imported at runtime. So printf might be in there if you use printf, or whatever the functions you import from libc will have a jump will be inside the entries referred to by the jump rel. And then this is really important. This is the DT debug entry, which provides space for the dynamic linker to put in a debugging pointer, and this pointer refers to a debugging structure which is exported by the dynamic linker, which allows you to connect to a process, a debugger to connect to a process, and find out cool information about what the dynamic linker has done with this process, what libraries are mapped where, all of that stuff. And that'll be better covered later because it's really important. Then step 5, so we're still loading an executable. So it looks through the dynamic segment, it finds all the DT needed entries for all the shared libraries which are needed, loads them up, no worries, and it adds the libraries to what's called a link map, which is stored inside the DT debug entry. Okay, so that debug structure which I was talking about contains a link map showing all of the shared libraries inside the remote process. It then performs relocations for the global offset table and the procedure linkage table, which I'll talk about more very shortly. In fact, right now. The procedure linkage table is really important, and for the stuff we're talking about, it's going to be quite critical. You probably would have heard about it a lot. It's stored inside the PLT section of the executable, and it basically allows executables to call functions which aren't located at a known location at compile time. So basically, any shared library function is this way, like printf or something like that. And the PLT is a set of function stubs. So when an executable wants to call printf, instead it calls a function stub inside the PLT, which it knows where it will be, and at runtime that function stub is patched to be the real location of printf inside the executable. So if we look at this, there's actually a diagram of this here. The program is calling printf. At compile time, it ends up with a call instruction to the PLT, this printf stub. And then when the dynamic linker loads up the executable, it finds all these PLT function stubs and it patches them to refer to the real location of printf inside the shared library which it's loaded up. So that's how you can call functions when you don't know where they're going to be. So the dynamic linker performs the relocations, and this is usually done lazily, and that's important because what normally happens is that the dynamic linker doesn't, as soon as it loads up the executable, perform this link. It leaves the stub alone. It doesn't do anything. Normally, when the first printf call happens, it actually makes this resolution because it's an expensive operation to resolve the symbol. And that can be important from injectso's point of view. So this link is normally done only when it's required. So that brings us to the dynamic symbols and the dynamic relocations. How are we going for time? Okay, the dynamic symbols and relocations are stored inside the rel PLT section and the dynamic symbol section. And basically, this tells the dynamic linker what it needs to resolve where. An example there would be a dynamic relocation entry for printf if you were going to call printf, and it tells the dynamic linker what it needs to patch where. For example, in the case of printf, it would tell the dynamic linker that it needs to patch the PLT, the address of the PLT entry, to refer to the address of printf, the real address of printf. And we'll talk much more about this stuff later because it's important to the way injectso and some of these other techniques work. And just for reference, although it's not all that interesting to us, the global offset table is like the PLT, but it is not for functions. It's used for data, which you might access, which you don't know where it is at runtime. So stuff like standard error, error number, all that stuff which exists in shared libraries, you get to that through the global offset table. And the global offset table is referenced by the PLT on the Intel architecture, but it doesn't have to be, and on the Spark it isn't. So that's why you often hear people confusing them. People often say, oh yeah, I patched the GOT or I patched the PLT or whatever. They're not the same thing. It just happens to be that under Intel architecture they are interrelated for functions. But anyway, both the PLT and the GOT are targeted for attack inside format string vulnerabilities, which is probably where you've heard of them, because they're at a known location and they're very easy to patch using format string exploits. And you can do a lot if you patch those entries. I think we're getting towards the end of all this ELF stuff, so we've got some interesting stuff coming up, don't worry. The DT debug record, which is one of the records inside the dynamic segment, it's appointed to a structure, as I said, provided by the dynamic linker at runtime with debug information. It's normally examined by debuggers to work out the location of shared libraries so that they can work out that when the code goes off into some random address, they can work out, oh, that's actually inside libc and it's actually printf, which the person is executing, the program is executing. And the debug record shows the memory layout of the process. For example, which shared libraries are loaded where, and other information about them. And we'll talk about that in detail with diagrams and stuff a bit later. Okay, so fair enough. Now it's actually time to move on to the interesting stuff. We're going to actually start to talk about real techniques and real life uses of these techniques. So the first one, the most obvious one, is if you want to modify the way programs and processes behave, is to actually just modify the code in the file, patch the file. This is very, very commonly used under Windows to, like, when you see on all those sites like cracks and stuff for shareware, that's basically what they all do. They just patch the code in the file. And the basic process of binary patching is that you need to either modify the code which is there, like just write over it with new code, or you need to insert additional code and call the new code from the existing code. Modify the existing code to call the new code. When you're binary patching, basically you normally code in assembler so that you can binary patch it's generally easiest to code in assembler, but you can use C. It's just that if you do use C, the patch will be much larger, and it will also, if you use C, you can't use any of the standard functions. You can't call any libc functions. You can't call string compare or anything. So it's almost pointless to use C, but if you want to, you can. So you code in assembler, and so now you've got this code and you need to get it inside the target executable and make it do something. So the first idea is, where are you going to put this code? Fair enough, you may have generated a K worth of patch, but where are you going to put it? There are a few options here. You can overwrite unused code inside the executable, which obviously is fraught with difficulty because it's hard to identify code which isn't used inside the target executable. I mean, generally there is lots of it, but it's hard to work out which code paths will never be called. And if in some weird situation the code path is called and your patch is there, it'll just melt down. Another option is section padding. When you've got an ELF executable, in between each of the sections, there is a very, very small amount of padding, generally less than 32 bytes, and it's used for padding to byte boundaries, like 32-byte boundaries. And you need a section which is inside an executable segment and all that stuff. It's not really a particularly good idea. I've never seen anything which actually does it. One option, obviously, which might strike you as the most obvious option, is to add a segment, because as we specified, the segment table specifies which bits of the executable are loaded where. So you can just, shove some code onto the end of the executable, add a new segment, get it loaded, and everything will go. So that seems like the most obvious thing, but it certainly isn't the best idea for reasons I'll explain shortly. And there are heaps of other methods. There have been a number of excellent papers written about all this stuff, believe it or not, in regards to Unix viruses. And some of the ways which they describe in those papers are better than the ways I'm going to describe. But the way I'm going to describe is the most obvious at first thought. So our example, our demo, is going to add a new segment to a program. There are a couple of options which we can do when we're adding a new segment. Obviously, we need to get our segment inside the segment table so that it will be loaded. So we're going to add code to the file at the end of the file, and then we need to have the segment table refer to this part of the file and get it loaded into memory. So the first process of getting our segment inside the segment table, we have a couple of options. We can either reuse an existing but unneeded segment. You know how I showed you the segment table list, and one of the things inside there was the PTP header segment type, and that segment, all it does is it refers to the location in memory at runtime of the segment table. It's not actually used. I'm not exactly sure why it's needed, but I haven't found a case where it's actually referred to by anything or it's necessary. So you could overwrite an unneeded segment entry which already exists, or you can just, again, take away which might seem more obvious and just create your own. Just modify just ignore all the existing program headers and create your own program headers. So this is basically what we're going to do. We've got the ELF header, okay, and we're going to patch the binary program, and we're going to patch the header, and the old program headers are still going to be there, but we're just going to add stuff to the end of the file and patch the existing ELF header to point to our new program headers down here. So we're going to have our own program headers, which continue to have all of the normal entries. So we copy all the old program headers down to here and add a new entry, make the table longer. So we have all of the normal segments, and then we're going to add a new segment right at the end of the file and refer to that inside the segment table, inside the new segment table which we construct. Now, it doesn't actually work that cleanly, mostly because there are major problems with the loaders. Most of the loaders inside a lot of the Unixes are very bad. They don't follow the spec at all, and if you actually do this, it doesn't work properly, but I'll explain that as I do the demo, and there are ways around it. It just makes it complex and annoying, which makes some of the other ways better. But anyway, so once we've patched, what are we actually going to do? I mean, what can we do if we patch a binary? We can do anything. If we have an understanding of the binary, if we've disassembled it, we can make it do whatever we'd like to. We can patch the function prologues inside the program so that we can make function calls inside the program refer to our new code so that we can modify the way the program behaves, or we can just modify code anywhere we like to insert, remove code, change the functionality, make it better, whatever. So the basic process which we use here is that we modify the old code so that instead of doing what it normally does, it calls our new code. So it does a jump to our new code, then our new code jumps back at the end. So a quick demo of binary patching. Okay, basically I'm going to use a really simple and trivial example here because but the technique does work on much larger and more complex programs, but it will be clearer if I show it on a simple program. Basically, I've got this silly little example of this program, which it just pretends to be a login prompt. Okay, so whatever. Doesn't actually do anything interesting, but it pretends to be a login prompt. So the most obvious thing which we're going to check for is what if this login prompt has some security vulnerability, like that. Okay, so it segfaults when it receives a long username, which immediately we suspect is because it's got some sort of buffer overflow vulnerability or something like that. So if I run login demo, what I'll do is in another window, I'm going to trace I'm going to do a library call trace. I'm not sure whether you guys are familiar with ltrace, but it is an awesome program, and it basically allows you to trace calls to dynamic functions from a program. So if I do an ltrace of the login demo, and I just type that. Okay. Inside my other window, I can see that what's happening is that it's obviously chopping off the /n on the username. Then it does a bare string copy, and then it asks for the password, and then it does a bare string copy. So this is like your completely extinct and trivial example of a buffer overflow. So what we'd like to do here is that we'd like to make this program non-vulnerable. We want to patch it so that it's no longer vulnerable to this obvious security problem. So what we're going to do is, the first thing we're going to do is we'll load in login demo here so that we can get an understanding of the executable. Just hold on 2 secs. Okay, so now if we go, this program still has the symbols, which obviously most processors wouldn't, but it will make it clearer to show what I'm talking about. Okay, so if I go to main, this is the disassembly of the main function. Okay, we can see f put s, f flush, obvious things, f get s to read in the string, work out the length of the string, and here we can see the bare string copy. And we can also see that its target argument is the base pointer -10. So basically we can tell immediately that the size of this buffer, it's on the stack and it's 16 bytes long. Okay, so if we go down further and we look for the second string copy, we can see the second string copy, it's EBP -20. Given that we know the other one was EBP -10, we also know that this is another 16-byte buffer on the stack. Okay, so obviously what we want to do here is we want to replace these calls to string copy with something safer. We want to make them length limiting. We want to prevent them from causing an overflow. So let's take a look. I just want to quickly show you. I use readelf here to look at the internal structures of a elf executable. Readelf is excellent. Try not to use object dump for this stuff if you ever do get interested in this. Object dump is nowhere near as good because it relies on the section information, which isn't always present. So we've got, this is actually looking at the program headers. You know how the loading view, and we can see all the segments here. Now, one of our options would be to overwrite one of these segment entries, like note is an obvious one, or p header, but that's not what we're going to do here. We're going to patch the executable to make the calls length limiting. Okay, so the first thing we're going to do is we need to add a segment to the executable. For that, I'm going to use a utility I wrote called add segment. Okay, login demo. I'm going to call the new executable patch login demo. I want to create the segment, and the new segment should be loaded at 9 there, and I want it to be 1024 bytes long. Okay, so now what this executable has done is it created a new executable called patch login demo, and patch login demo has a new segment. If I do readelf patch login demo, okay, you can see that it differs from the old one in that it's now got this new load segment at the end. This load segment will be loaded at the address I specified, and it will be read, write, and execute. Okay, so I've added a segment into this executable to give me some space to patch something in. One thing you'll also notice is that if I do the readelf on login demo, see how this has got a mapping between the sections and the segments. Add segment, just as a demonstration, also removes all section information, which means that object dump will never recognize this file. It has no section information. So as far as it's concerned, GDB and all that stuff will never work on this executable. It's not an executable. Okay. So I've now got some space to work in. What I'm going to do is I'm going to use patch. What do I call it? I'm going to use, can anybody see this stuff? It's coloured. Is it easy to see still? Yeah? Okay. Anyway, I've hacked up this quick little bit of assembler. Don't pick on my assembler. I'm not that great. But anyway, I've just hacked up this quick patch, and what we're going to do is we're going to patch all of the calls to string copy and replace them with this code. Okay. What this code does is it calls our new patch. Okay. Then our new patch replaces the current call to string copy with a call to this new thing, a strul copy, which is just an assembly implementation of string L copy, if you guys are familiar with it. Okay, so basically all I do is I'm going to patch in a string length of 16 into the executable so that it will, and then call string L copy, which I'm going to patch at this address. And so basically instead of calling string copy, it will call strul copy and be safe. It will call it for 16 bytes once I patch this executable in. Once I patch this, code in. Okay, so the first thing I need to do is I can see that the first call to string copy happens at this, first call to string copy happens at 804.855D. Okay, so basically what I do is I'm just using utilities here which I've got to rip out bits of code and to apply them. So I'm going to construct a patch. Okay, my patch is just, let me check that I don't have. No, cool. Okay, so code patch add login patch. The address I'm going to want this to be patched at, which is 804.855D, which is the address of the first string copy. So I'm going to replace the first call to string copy. What I want to patch there is I want to patch something from fix login demo.o, and I want to patch the bit which calls the new patch. Okay, cool. I need to do that twice because there's there are two calls to string copy, so I'm going to apply the same patch to call our new patch again at the other address, which is 804.85C9. C9. Okay, cool. So I've now I'm constructing a patch file here. So I've got two patches at the moment to call my new patch. Now I need to actually put in the actual patch itself. So to do that, I just I specified that it would be at this location. And fix login demo. This time I'm going to actually put the patch in itself. Okay, cool. So I've added the patch, and now I add the add strul copy, the A strul copy, which I spoke about, the assembly version of strul copy. So A strul copy. There we go. Okay, cool. So I now have a patch file which consists of patches over the old calls to string copy, which to make them point to my new patch, which calls strul copy instead. So now that I've got this patch file, I apply it to my patch login demo. Code patch apply patch login demo login patch. Okay, so I've now applied the patch onto the executable. As you can see, it just read in all the patches, went that, put it onto the actual executable file, like that. And now what I should have is I should still have, okay, so I've got like a normal login demo, whatever, it continues to work as normal, as we can see, but no longer segfaults. So basically I've just modified this program. Instead of calling string copy, it now calls strul copy so that it's safe. So I've removed the vulnerability from this program. How am I running for time? Okay. So what are the advantages of binary patching? Binary patching is extremely flexible. You can do anything you'd like to this program. And that's why it's a very common technique. It's permanent, so this program will never be vulnerable again. Okay, it's like if this was a set UID program, it would continue to work, it's fine. Okay, permanent, and it has very little performance impact. That is, it's extremely quick. All I've done is added a few extra instructions. It's very fast. Okay, so that's binary patching. What about its disadvantages? This is hard stuff. This is not easy. It's complex, it's error prone, it's time consuming, which makes it very much something for people who are experienced, either that or people who've got a lot of time on their hands. particularly the ASM code and the disassembly, and it can also be dangerous if you get it wrong. You can easily end up with weird situations where you've just destroyed the program. It's very hard to intercept dynamic functions because you can't overwrite PLT entries, so you can't intercept all calls to printf very easily because the PLT gets overwritten by the dynamic linker, and the program has to be restarted. So if this is bind and you're a really large ISP, you can't do it. You have to restart the executable, and that's not going to be allowed. You're going to have to wait a week to apply a patch, whatever, until you can get some scheduled downtime. So that can be a big problem with this stuff. Further disadvantages, the program executable has to be modified, which some people find a bit scary and want to avoid, and the entire code which you end up patching in has to be relocatable. That is, you can't easily call dynamic functions like printf or anything like that. You can do it, but it's hard. If you saw the worm presentation, you would have seen that you have to construct your own import address table, although under Unix obviously you'd construct your own PLT. So you can't easily import functions. And you end up having to make most syscalls directly, and so I don't know, it's something to be avoided unless you've had some experience with it or feel comfortable with it or have some time to do it. Previously I was going to speak about dynamic linker stuff now, but I'm not going to because I think in-core patching rolls straight on from it. In-core patching is basically where we do the same idea, we patch the executable, but this time we're going to patch it while it's in memory and it is still running. Okay, this is reasonably obvious. All we have to do is we have to connect to the remote process as a debugger using ptrace or procfs, depending on what's provided by our operating system, and then we're just going to manipulate the program's memory remotely. As with static patching, we have the same needs. We need to be able to insert additional code, and we need to be able to link the existing code to our new code. So the question becomes, as it was before, where do we put additional code? Well, obviously, we need this code to be inside a memory page which is marked as executable. We have a couple of options. We can overwrite existing unused code, again, find it. We can use the segment padding rather than the section padding. Segments are padded, loadable segments are padded to page boundaries, so that's normally 4096 bytes on most architectures these days, which actually means that we have quite a significant amount of segment padding. It's quite useful. And it's a fairly obvious option. We can, or one other option, which is weird but could actually be interesting to some people, is that, you know how I said that there's the P header segment, which contains the program headers at runtime, but it isn't actually needed. For some reason, most compilers mark that segment as executable, and they put it inside an executable segment, so you can actually overwrite the program headers at execution time, and because they're not needed, and just use them. So they give you a little bit of space if you're desperate. But and linking in the additional code exactly as you did with file patching. So basically it's very much like file patching. You just have different requirements for finding space inside the remote process. So looking at this one. Okay. So we'll just patch login. We don't need that anymore. Okay. So if I look at login demo again, okay, what we're looking at here is we can see that we've got these loadable segments. One of them is readable and executable, the other one is readable and writable, but you'll see that both of them are aligned to a page boundary, 4096 bytes, the alignment field, okay? And so what that means is that this segment here, which is executable, it's the actual code of the executable, it's only 642 bytes long, but it's padded to 1000 bytes long. So we can actually use all of that space in between since it's guaranteed to be in memory, but it's not used by the executable. So that's where we can place our stuff. So if we just (0x). So the thing is there, but it's only 642 long. So we can start our patch at for example, 8048.700 or whatever. We've got plenty of space, heaps of space there. So again, we're going to construct a code patch, but instead we're going to apply it on the... Do you have a question?
Excuse me, isn't that page not writable?
Okay, yeah, that's an interesting question. It's true. When you connect as a debugger using procfs or ptrace, page permissions no longer count. actually what you'll see if you actually look at kernel code for this stuff is that the kernel, when you make a request to write to some memory inside the remote process, it will automatically disable page protection on that page, apply your patch, and then re-enable page protection. There was a bug in old Linux kernels which didn't reapply page protection, which led to weird problems. But basically, no, you're not subject to any restrictions inside the remote process space. Otherwise, debuggers wouldn't be able to do all the cool stuff they do. So anyway, so we've got plenty of space. We've got heaps of space. So we're going to construct a normal code patch. And we're just going to actually this time instead of fixing the process, let's actually do something different with it. What a black hat might do. Let's actually see if we can backdoor the process at runtime. So to do that, we're going to use okay. Am I running out of time? Yeah, I am. Okay, so I'll have to go really quickly through this. Anyway, this is another assembly patch. Again, I patch a call to string copy. Okay, I patch it to point to this patch. What this patch does is it calls strul copy as normal. This assembly strul copy. So in the process of backdooring the process, it actually fixes one of the overflows. Then after it's done that, it checks to see whether the string. Here it checks to see whether the string which was copied is actually the string let me in. Okay, if the string was let me in, then it calls where am I? I can't see. Oh yeah, sorry. Yeah, if the string was equal to let me in, then it falls through to here and it calls shellcode and it throws a shell. So basically, this is a magic login style backdoor. Okay. So I'll construct a patch. Cool. So code patch add. Okay. I'm going to construct a new login patch. This time I'm going to patch inside that segment which we were talking about. 700. And I'm going to patch patches. Login demo.o patch core patch. Okay, cool. So I'm going to apply that patch. Actually, the first thing I should do. What am I doing? Code patch. First thing I'm going to do is I'm going to patch over one of the the first string copy, which, as we saw before, was at 804855D. Okay, so to do that, I'm going to take and I'm going to patch that with call patch and end call patch. Okay, cool. Then doesn't matter. Then I'm going to patch in the full patch at 8048,700. End patch, okay. Then I'm going to copy in a strul copy. A strul copy. And I'm going to copy it to 804.800. Cool. Then I'm going to copy in an assembly version of string compare. And I'm going to copy it to 804.8.900. Okay. That. And then I'm going to copy in the shellcode to 8048A. Cool. So now what I'm actually going to have to do is I'm going to apply this to the running version of login demo. Okay, cool. So login demo is running. Okay. Code patch core. With specifying the PID and the login patch. And I hope this works. Oh, sorry, it was login typo. Yeah, okay. Anyway, so basically what it does is it took the call patch, size 8, applied it to that virtual memory address, took the actual patch itself, applied it there, took strl copy, applied it there, took string compare, applied it there, took the shell code and applied it there. Okay. So what should now happen is that hopefully the program won't crash. Okay, cool. So I have to apply it again, obviously, since it's applied at runtime. So if I apply it again, this time we should actually see that the first, by default, the first buffer overflow should be fixed. So let's see whether that's the case. Doesn't. So okay. So we've dynamically patched the first buffer overflow vulnerability, but much more evilly than that, we've done this. Yep. So you can see that it throws a shell. So if you use let me in, but it's thrown a shell there. So basically you can dynamically at runtime also patch vulnerabilities, but also introduce backdoors into programs. So that's demo 2. I'm running really late on time. I apologize for that. It's a bit bad because we started late. But okay, so what are the advantages of in-core patching? In-core patching is very flexible. Again, exactly like patching executables on disk, you can do anything you'd like to with it. It's non-permanent, which is, in some cases is a big advantage. There are times when you don't want this stuff to remain, and it can be performed on any running process, which is obviously its big cool thing. What are its disadvantages? It has exactly the same disadvantages as it does as you do have for file patching. It's complex, it's error prone, and it's time consuming. And it's much more dangerous than actually patching on disk too, actually. You can very easily kill the running program. If you change something which is in the process of being executed while the program is still running, very easy to kill it. If you get it wrong, it's dead. You know, you have to be very careful when you're doing this stuff. It really is error prone and time consuming. So okay, so believe it or not, we're now actually going on to the simplest form of modifying programs and processes, which I'm going to talk about. Okay, so we've talked a lot about the dynamic loader, okay, and how the dynamic loader it resolves all of these external symbols for you, okay. In fact, it resolves all of the dynamic relocations which refer to the GOT for the data relocations and the PLT for the function relocations. How does it work? Okay, well, as we said, the first thing it does is it reads in the DT needed entries and works out which shared libraries are required. It loads them into memory, okay, adds them to a thing called the link map. Then it goes on to process the relocations. So if we actually look at what the link map looks like, we can see this, okay? If I have a test program, okay, it's in the link map, and there's a pointer to the base address where this program is loaded, okay? If I've got libc, which all C programs have, then there's a pointer to the base address of libc in memory. At libn cursors, for example, pointer again, term cap, pointer. So basically the link map tells us the structure of the program in memory. So how does it actually resolve things? Well, when it's processing a relocation, the dynamic linker looks through this map, okay? It's looking for a certain function. Let's say it's looking for printf, okay? It searches each of the library's exported symbols, all of their dynamic symbol tables, okay? It tries to find a matching symbol name, and it tries to find a matching symbol name which is not declared as a weak function. And the first match which it finds is the winner. So in other words, it looks through the link map sequentially, tries to find a match. If it finds a match, boom, that's the resolution, and it resolves that function. So the trick to doing interesting things with the dynamic linker is to be the winner. The trick is to get your library loaded first, so that whenever the dynamic linker is looking for a dynamic function, which as I said is normally done lazily, when it's looking for something, your library will be the supplier of that function, okay? So your library, if you get it loaded first, it will be the winner for all of its exported symbols. And it can therefore intercept any dynamic function call. For example, a call to printf or any other libc function or whatever the function you'd like. So the question then becomes, okay, I can now intercept dynamic function calls. How can I get in first? there are heaps of ways to get in first. One of them is to modify the DT needed records. As I said, the DT needed records specify which libraries are required. Okay? If you modify these records and you make your library the first one, you'll be mapped in first, and you will therefore always be the winner for any symbols you export. And to do that, you can just overwrite another library entry for some other library which is required, and then inside your library, you can be dependent on that other library. So you don't destroy the executable. You just overwrite one of its dependencies, and then make one of its dependencies one of your dependencies, so that all of the stuff still gets loaded, but you just happen to be first. Another option is to move the dynamic segment and recreate, so that you can add an entirely new DT needed entry without overriding an old one. And then the most obvious one, and this is a very common technique, you probably all would have seen it if you're familiar much with Unix, the LD preload environment variable specifies the names of libraries which should be loaded by the dynamic linker before all other libraries. This is really commonly used. If you've seen any of the stuff which transparently soxifies applications or anything like that, that's how it all works. It gets its library loaded first, and it overrides libc functions. God, okay. So I'm out of time for the first half. Did you guys want to keep going and see the demo of this stuff, or did you want to go get coffee and try and squeeze it in on the other side, or not interested in it? What's the idea? Keep going? Yeah? Okay. So basically, once you've got your library in first, you can intercept all dynamic function calls. Okay, so that's cool. But usually what you'll need is your intercepting function will need to call the old function, and that's really easy because the dynamic linker provides you a couple of functions. One of them is dlopen to open a library. The other one is dlsim to get the address of a symbol in a library. And if you specify rtld next instead of giving it a library, the dynamic linker will tell you where that symbol is located in any library which was loaded after you. So that makes this really trivial. So all you do inside your code is you ask the dynamic linker using dlsim, give me the address of this function in a library which was loaded after me, and you can then call the old function. So let's take a look at this example. Because LD preload has been well and truly done to death, I'm actually not going to do LD preload because it's boring. But instead, we're going to do this various manipulation of the DT needed entries. If you'd like, I have two demonstrations here. We can just do one of them, or we can do both of them, or whichever one you'd like to do. We can either fix the demonstration program using this technique, we can backdoor the demonstration program using this technique, or we can do both. Which would you guys like? Audience participation. Would you like to see it fixed? How'd I know everyone would say that? Okay, so let's backdoor the thing. No worries. So what we'll actually do is we'll do the most advanced way of doing this then. One of the obvious ways which you can do this, if I load up BIEW, I'm going to get out of this. And if I go into hexadecimal mode, what I can actually do is I can find inside here, if I just hold on, I'll do the -D. So I'm going to look at the dynamics. Okay, so you can see what I was talking about. See the DT needed entry? It specifies the shared library which is required, and in this case, it's libc.so.6. One of my options is to simply overwrite that string. What I can actually do is I can overwrite libc.so.6 and point it to my new shared library, and that shared library can then be dependent on libc.so.6 to make sure that it's still loaded, the requirement is still loaded. The problem with that is that if I overwrite libc.so.6, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes there at all. That's all I have, 9 bytes. That means that I could only patch it with something like extremely short, like fix.so or /tmp/f.so or whatever. You don't have much room in there, which can make it an annoying way to go. So I'm going to show the most advanced way, and what we're actually going to do is we're going to completely relocate this program is going to it's going to add a couple of new segments to the executable, it's going to completely relocate this entire table, and it's going to add a new string so that we can specify as long a library as we really want, which this is actually really non-trivial and it's quite difficult to make work, but it does work, so let's demonstrate that. Okay, so what we have is we have libs, and we've got okay. Now, so basically, obviously you can see this is really trivial code. There's nothing special here. We have a function pointer to the old string copy, our replacement string copy here, a declaration of our replacement string copy. We're in our init function for our library, we get the address of the old string copy using the RTLD next, which I was talking about. Okay, then we have our replacement string copy, which will always win. Remember, we're always going to be the string copy because we're going to be the first. Okay, then all it does is it string compares what's entered with let me in. If it's let me in, then it just execs a shell. Otherwise, it calls the old string copy. Okay, so it's trivial. It's like, I don't know how many lines that is. Like 10 lines or 15 lines. It's just ridiculously easy. And patching it and fixing the problem is as easy. Just let me quickly show you that. I won't actually run it, but I'll just show you that. I mean, I went a bit advanced here, but basically you do exactly the same thing, get the old string copy, then I just checked where we were called from. If we were called from a vulnerable string copy, then I called string end copy. So no worries. So what we're going to do is we're going to modify the login demo using add library. So if I go add library, login demo, God, my typing's not going well today. New login demo, okay, and what I'm going to specify that I want this to be. Okay, so I want to add this library to the dependencies of the executable. So if I do that, basically what this, I mean, if we look at the, just let me quickly show you what I mean here. If we look at the old login demo, like that, and we look at the new login demo, what am I doing? Did I read elf -l? Yeah, anyway, sorry. And you can see in the process of adding the new library requirement, I've had to add a new segment here onto the end, exactly like before, except now it's at a different address and all that sort of stuff. But basically this new segment contains this new requirement, this new dynamic library requirement. So if I do a read elf -l of the old login demo, sorry, -d. Okay, so you can see the old one. Okay, see how new login demo has a new DT needed, and the DT needed requirement is this. With the full path, so we can see that now this will always be first. As you can see, it's the first DT needed. I'll always get in first for any library I export, and libc is second, so I will always get string copy. So if I run this. New login demo, okay, so whatever, you know, it just continues to run as normal, but it's now got our library inside it. So if I go, let me in, the magic username, it just runs a shell. So that's trivial. That's a really easy way of modifying a program, making it do cool stuff. And it can also be very easily used to fix programs or to backdoor it. All of this stuff, all of this technology, if you can use it for good, you can use it for evil. So I guess just try and use it for good. So anyway, what are the advantages of the dynamic linker tricks? All the interception is done in C. It's easy, it's simple, and it's safe, provided you write good routines to replace the old ones. Okay, LD preload the LD preload method is non-permanent. The disadvantage of the dynamic linker tricks, well, you can consider it a disadvantage that it's not permanent. The DT needed approach requires modification of the executable and the new library to be in place at all times. Okay, because you've added this dependency. If this library goes away, the program will cease to work because it's got this new dependency, and the program must be restarted. Again, it's not very good if you've got a bind and you need to patch it and you're a major ISP. You simply can't do it. So that's the end of part one. Are there any questions, or is everyone in a rush to get a coffee? Okay, cool.